Good morning, everyone. We are welcome to the Symposium NGS-WQM 2019 again. So this is season 4 time. I would like to invite Chair of Symposium, welcome Associate Professor Dr. Sae-Lim Vinitnantharat on this symposium.
Good morning. Good morning, Assistant Professor Dr. Kuskana, Kubaha, Dr. Panya for Fisheries, Dr. Sae-Lim for National Science and Technical Development Agency, Dr. Werner for Newcastle University, Dr. Panya for Vietnam National University, Ladies and gentlemen, on behalf of the workshop committee, I would like to sincere thanks all participants for coming and trying hard for the VCM media, particularly for today 73 participants from 70 institutions are here, including researchers, students, faculty members from 9 universities, Fisheries Department, Bangkok Metropolitan Administration, National Science and Technology Development, Aquaculture Magazine, and Marine Leader. The symposium on next generation sequencing and probiotics and other technologies for water quality management in aquaculture is one of collaboration research activities under the Newton Fund institutionally. It was organized by School of Energy, Environment and Materials, School of Bioresource and Technology, Pilot Plant Development and Training Institute at Mongkut University of Technology and Newcastle University, Newcastle upon Tyne, with the financial support from Office of Higher Education, Commission, and Business. The objective of this symposium are firstly, to exchange the knowledge and experience on the research related to environmental sustainable management. Secondly, to foster the academic collaboration among the researchers from universities, government agencies, private sectors, communities, and experts for a board. We invite two keynote speakers, Dr. Werner. He will present the novel microbial water quality monitoring network, which you will know more about next generation sequencing technology and how to apply for aquaculture research. And Dr. Panya will let us know about the management of aquatic animal populations and genetics. During the morning session, there are the overview of aquaculture farming and management, as well as the research results done in aquaculture farm. Finally, there will be a panel conclusion and discussion by Dr. Werner. I hope that this symposium is not only bring your friends to be here, but also make new friends from other organizations. We plan to have a series of workshops and symposium related to sustainable management for aquaculture farming for the whole year, as we will celebrate the 60 years anniversary of the university in next year. I hope that we will meet again. Thank you very much.
Dr. Sae-Lim Vinitnantharat. For the next, I am pleasure to invite Assistant Professor Dr. Kuskana, Kubaha. He is Dean of School of Energy, Environment and Material. Welcoming speech to participants and opening this symposium.
For Newcastle University, they are from Vietnam National University, maybe in Germany. And I'd like to be here to join open symposium of regulations addressing probiotic and other technology over the quality management of aquaculture. On behalf of the School of Energy, Environment and Materials, University of Technology, Thonburi, I would like to extend my moment will come to know. Ladies and gentlemen, Aquaculture provides high quality and safe nutrient food for Cooperatives all around the world. Each fast growing among the food sector and continue to grow as the world population increases and infection increasingly applies. The demand is increasing while the production is restricted by many factors such as climate change and systematic urbanization, industrialization, which affect the water quality and coastal farming and aquaculture. It is a challenge to maintain global food security and sustainable increase production with minimal environmental perturbation. Since aquaculture farming use high volume of water resources, urbanization and industrialization will bring heavy metal, toxic residue, organic waste, and pathogen treated to the aquaculture animals. Water quality and microbial diseases are key factors for the success of aquaculture production. Methods to combat microbial diseases in aquaculture involve the use of antibiotics and disinfectants like chlorine, but these methods are highly controversial. Chlorine discriminates both good and bad bacteria today and make them prone to colonization by fast-growing bacteria such as really pathogenic microorganisms. The excessive use of antibiotics may cause antibiotic resistance. The microbial resistance is one of 5 priorities to identify by Ministry of Public Health of the Thai government, then it is necessary for more sustainable safety management in the population. Ladies and gentlemen, we as academic institutions, we mobilize for joy and in helping the world. For experts here, we deeply know that boosting the share of management tool and technology requires a breakthrough on technical difficulties. These challenges truly need research, a clear grasp in the technical know-how on managing the sustainable management under climate change in aquaculture. Farming has to be a digital skill that should be passed on to farmers, direct community, local and national and international policy makers with the assistance of scientists and engineers. I am glad that many top scholars are sitting here to share ideas and exchange knowledge, contributing to the development and collaboration and advancement of next generation sequencing technology, probiotics, and other technologies. Ladies and gentlemen, School of Energy, Environment and Materials is proudly to host this symposium, which is organized by Prida of Mongkut University of Technology and Newcastle University under the Vinitnantharat institution. Our university will celebrate the 60th anniversary next year as transforming society, defining the future. So this symposium will provide valuable information for all of you to further research and help the society. As for the school, we are the first school in Thailand that deliver related courses. Throughout our 40 years, we have produced about 4,045 postgraduates working in government and non-government organizations around the country. we have been networking with the school. We joined Graduate School of Energy and Environment, School of Bioresources and Technology, Pilot Plant Development and Training Institute, and also other outside organizations, including academic institutes and government offices. In particular, the Ministry of Energy, the Ministry of Industry and Bangkok Metropolitan Administration. We are seeking for more alliances. Today, we have experts from the United Kingdom, Vietnam, and Thailand to share knowledge and ideas of different views contributing the next generation. Sequencing technology, probiotic, water quality, management, biochar utilization, and microbial. I hope that this workshop will provide an open forum for discussion and essential issues. Your comments, involvement, and expertise will make a productive workshop. I wish that there will be a fruitful discussion leading to a series of valuable collaboration in the future. Thank you very much.
For the first keynote speaker is Professor Dr. David Werner. He is a reader in the School of Civil Engineering and Geoscience at Newcastle University. His group at the Newcastle University performed research in environmental engineering with a focus on modeling the fact and remediation of organic pollutants in natural and engineering systems for the optimization of the water, soil, and sediment treatment design. Additional research strengths of his group include the use of metal in treatment, magnetic or integrated solvent for water treatment, the use of plastic sampler for environmental monitoring, the use of enzyme in wastewater treatment, and the protection of water resources from fire and diffuse pollution. Today, he will present on the topic novel microbial water quality monitoring method and the application to aquaculture. Please welcome.
Thank you all for coming. It's really my pleasure to be back again. It's been a very good collaboration with KUPT, and today I'll give you an overview of what is done so far and what we intend to do with this new project. We try to look at water quality, microbial water quality, and how we can measure it, and how we can apply these monitoring methods to better water quality management. There's a very long list of people down here. So all of these people actually help with the work. So I know much less than some of these people here. We'll hear our presentations later. Just to give you some background of where we come from, we do some work across the globe, including in Africa, on water quality and how we can assess water quality. And what we try to do is develop methods that we can apply anywhere in the world. So we're trying to develop what we call a portable laboratory that we can put in our suitcase. Then we can go to Thailand, we can go to Tanzania, we can go to Nepal, we can go to India, and we can analyze the water quality anywhere we go. So that's what we're trying to develop. This is a little overview of how we are approaching this. So we try and take water samples. This is the work that we're doing in Africa. Then we filter in. These are tanks that you can put into your suitcase. And after the filtration, we can do some classic microbiology. But we can also extract DNA, where we talk about this a little bit more. Once we extract the DNA, we can use different methods to look at this DNA and learn from the DNA what type of bacteria we've got in the water. So we've got a mini PCR machine, which is about this size. We can put it in a suitcase, allows us to do PCR. And we've got the MinION, which is a memory stick size sequencing device. We can also do this we can use this portable equipment. So what we want is within 24 hours, we want to be able to report the water chemistry, the water microbiology, and do all of this in a portable laboratory. So that's what we're trying to develop. And this is just one application that we are using this for, which is to work with you here in Thailand and Aquaculture. Our first engagement with KMUPP was with funding from the Newton Fund on using agricultural wastes for water pollution. And as part of this work, we looked at water quality in some aquacultures just between Bangkok and Coast. And the way we look at the water quality is that we would look at the quality of the water in the canals and compare it with the water quality in the ponds. So the farmer, they will take water from the canal in their pond, and then they will discharge some of this water back into the canal. So basically we take samples here, we take samples here, and we compare the water quality. Initially, our thinking was that the aquaculture is polluting the canal. So as you may see, now we think that the canal is polluting the aquaculture. So we looked at different types of aquacultures. One is extensive aquaculture, which is without addition of any nutrients into the ponds, semi-intensive and intensive aquaculture. So if it's P, it's the pond, and if it's C, it's the canal, if it's E, it's extensive, if it's S, it's semi-intensive, and I is intensive. So that's kind of the daily I use. So we took some samples in June 2017 from the ponds and from the canals. That's the type of measurements we did. We did very classical culturing data. And this allows us to see what bacteria we have and compare with some standards. But we also use qPCR, which is a DNA-based method, and we use sequencing. So these are different approaches, and they each have their advantages and limitations. And we think it's best to use all of these methods in parallel, because each method gives you a different type of information. So what we can get from the sequencing is basically an understanding of which bacteria do we have in the water. So we can look at all of the bacteria. This method will give us an identity of what type of bacteria we have in the water. qPCR allows us to look at specific bacteria. If we look for pathogens, for fecal pollution, If we look at functions such as toxicity, but also beneficial functions such as probiotics, then we can use this method here. Culture we can use to look at whether or not the bacteria are alive, or maybe, because with these methods we don't know if the bacteria are alive. So I'm just going to illustrate some of the results from these different methods, how they agree or how they disagree, and how we can learn from them. So this is the conditional paper count results for fecal coliforms. There are some guidance on what you should have with water that you use for aquaculture. So your standard here in Thailand for coastal aquaculture is less than 70 fecal coliform units in 100 milliliters of water. These are the results. You see that at least 1,000 times more than that. The water in these canals in the aquacultures have much more fecal coliform pollution than you would like to have for aquaculture. And you can already see that it's typically the sea, the canal, that has a higher concentration than the pond. So this is extensive canal pond, semi-intensive canal pond, here is the intensive canal pond. So the extensive pond has the lowest count, but the canal for this aquaculture has the highest count. We can also look at this with more fancy technology. So this is now sequencing. And we get the same result. So with sequencing, we can look at all of the bacteria, and then we take out the bacteria that we think are related to the gut. So in the gut of humans, you've got these type of bacteria. Phylloxera, Campylorides, bacteria. Then we can estimate the abundance if we know how many genes we have with the sequencing. And we get the same results. So this is the canal, this is the pond, this is the canal, this is the pond, this is the canal, this is the pond. So there's a lot, especially these type of bacteria that's from the human intestine, we only find in the canal, or much higher in the canal. So that's strong evidence that we've got domestic wastewater in the canal, but some of it we had into your aquaculture pond. You can also see for these bacteria here, E. coli for example, if you have an intensive aquaculture, you also have relatively high numbers of those. But we don't see these bacteria, which is in the intensive sea bass. That's the type of information you can get from sequencing. You get a lot of other information as well. This is just an example. This is qPCR. So with qPCR, we can now look at E. coli, but also see whether it's from humans or animals. These are results for E. coli from humans. And now on, now on, now on. So again, there's a lot more human E. coli in the canal as compared to these aquaculture ponds, but there is some input. So there's some exposure of the pond to this fecal pollution in the canal. So there's about 1,000 human E. coli in 100 ml of canal water. According to these measurements. Then we can also look with qPCR, you can for instance look at resistance genes. So we look at genes that code for antibiotic resistance. And we just started this work, so it's still ongoing. We haven't finished yet. But again, it's the same result. So we find antibiotic resistance genes for tetracycline in the canal, not in the pond. We find it in the canal, not in the pond. So when we started, we thought that the farmer is using tetracycline, which is creating resistance, and then discharging into the environment. And the result is the opposite. Actually, the resistance is already in the environment because of domestic wastewater pollution. And the farmers, they told us they don't use antibiotics. So from this technology, we can learn where the source is also for antibiotic resistant bacteria. We think in this situation, in this canal here, the main source is probably from domestic wastewater. It's not from the aquaculture. So these are the conclusions that we have from this work. So we have a lot of fecal coliforms, 1,000 times more than what is acceptable in principle for coastal aquaculture. We think that also this resistance is coming from the domestic wastewater, not from the aquacultures. Actually, these aquacultures, if you look at the data, they reduce the fecal pollution. So if you put the water into a pond, maybe because of the sunlight, you get some disinfection, and you return it back into the canal, it has better bacterial quality. So maybe especially the extensive aquaculture is a way of improving the water quality rather than making the water quality worse. Now, why are we having these type of observations? I think it's because we've got this huge metropolis, Bangkok, a lot of people living there, and we have only limited wastewater treatment. So there's pollution in the canals that comes from Bangkok and travels downstreams, and then it gets into these aquaculture ponds. And there's some risk then that this contaminates the food production, but also it's a risk to the people that work in these ponds. So we've got a lot of fecal pollution here, potentially with pathogens. It's a risk to these farms that work in this water. So we need to be aware of that. At the same time, of course, there's also opportunity. So, if you produce your aquaculture product close to the city, in principle, you don't need to transport it very far. Also, there's more affluent consumers. Maybe produce some sustainable, organic, healthy food here. In principle, that's a big opportunity. But you need to address this water pollution issue. So this leads us to the new project which we are working on now, which is on using these technologies to help improve the quality management by the farmers. So what we're going to do is we're going to look at six different farms. Two of the farms are the same that I just presented you the results. Some of these farms are the same, and we've got some additional farms. We look at water as well as sediment. So far we only look at the waters, we also look at the sediment. And we will look for 4 different times. So 4 times across. And Adrian will present the results from our first sampling in January. We just finished the second sampling earlier this week. And as we speak in Dr. laboratory, we've got the sequencing going on. So maybe by tomorrow we already have the results. So that's what we want to achieve. Thank you very much. And thank you to everyone who helps us with the work. It's all the people in the yellow shirts. Thank you all for your help.
Okay, thank you for our presentation. For the next, for the next speaker is Dr. Panya Sae-Lim. He graduated from the Faculty of Fisheries University with the first class of honor and was ranked to 82nd Louisiana. He decided to continue for the high education award. In 2005, he was awarded the prestigious King Scholarship or Anand Foundation from the King of Thailand. In 2006, he started to master program in animal breeding and genetics at Vinitnantharat University in Netherlands. In 2008, he graduated for the master degree and he continued for the PhD, which was a collaboration between Prida, USA, and Animal Breeding and Genomic Center. In 2011, he graduated the PhD and decided to do the postdoctoral research for 6 years in Netherlands for get more experience about his work. After that, I'm coming. Okay, sorry. Okay.
Thank you. First of all, I would like to thank the organizing committee for inviting me to give a talk today. My talk today actually about the application of NGS in selective breeding in aquaculture. So my class today is just to make you understand about selective breeding by 15 minutes. So it's really challenging for me, and I will try my best. And if you have any questions, just stop me during my talk either, so I can answer you there. I change the microphone. Okay, that one's better. Yes, much better. Okay, see to me. Alright. First, I would like to start talking about selective breeding. What exactly the selective breeding? It's just to select the domesticated animal to be as a parent based on your desirable trait or economically important trait. The selection criteria usually based on the natural difference on the trait, and that difference you can actually observe, you can call it phenotype. So each animal, they have different phenotype, and the phenotype, they are quite different. So basically, if you're looking at this animal or the fish, looking at the line, at the horizontal line, you can say that this is the generation of the animals. So if you perform selections, so say that you give the probability of some animal to be the parents for the next generation based on their performance or high performance, you basically improve the animal by, on average, of the animal in next generations higher than previous generations. And the difference between the average of the population is the genetic gain. So if you keep doing, the average of the population will increase. And alternatively, if you prefer the market size of the animal, so you can shorten the rearing period of the animal. So that is alternative way of using the selective breeding. If you don't do any selective breeding, passing by 5 generations, you still have the same average of populations. So this is much more efficient to have selective breeding in aquaculture. Selective breeding is the only approach that is generate cumulative and permanent increase in productivity in aquaculture. The importance of selective breeding, mainly to food security. Of course, aquaculture already contributes a lot to food security today, but selective breeding can make aquaculture to produce even more food. So, for example, if you're looking at this graph, 30 years ago, aquaculture for Atlantic salmon, it takes about 20 to 22 months in the seawater or sea cages to be able to achieve the production 4 kilo on average. Today, Atlantic salmon, they use a lot of selective breeding, and it reduces significantly the rearing period at the sea, to about 13 months, or let's say by 1 year, they can get about 4 kilo on average. And this reduce a lot to the feed, the use of the feed by 500,000 tons per year. And that's value about 5 billion krona per year. I mean 5 billion Norwegian krona in that year. If the selective breeding continue to happen, the reduction in feed also still going on. I'd like to also start with the selective breeding a little bit more in detail. So what exactly determines the phenotype? Basically, we all know about the very basic genetic models. The phenotype determined by two key components, which is genetic and environment. So we can observe the phenotype, but we have no idea about genotype. We cannot see the genotype of the individuals. We see only the phenotype. So if we want to understand the mechanism or the pathway of genotype to phenotype, we need to do molecular biology, molecular genetics, for example. But if we don't do that, this is what we call a black box. So we don't have any information about this pathway. We use the phenotype, which is observable, to predict the genetic effects of the animal. And this prediction, usually we try to predict what we call estimated breeding value, or the EDV. We select on the EDV, and the question you might already have is that, does it really work because we don't know any pathway about genotype and the phenotype? Is the prediction is good enough to be able to ensure that you somehow get a good genetic gain? The evidence of genetic progress already published for several years. This is for aquaculture. Of course, in livestock, you already have many documentations. The genetic gain per generation is varied among different species and also different populations and also different traits. But at least you can see that even with this prediction of estimated breeding value, it really works quite well. So the genetic gain varies from 7% to close to 20% per generation, which is really, really high. But unfortunately, it's not the same story for overall survival and disease resistance. Some of the disease resistance genetic gain is quite high, but for example, WSV, the genetic gain is quite low per generation. And the reason is the heritability is very low for this strain. The heritability explains the relationship between the phenotype and the genotype of the animal. So when the heritability is very low, it means that you can make a very slow progress, or your predictions accuracy is rather low per se. Now we see the limitation of prediction accuracies. So for some trade, you need to improve the accuracy to be able to get a better estimate of the breeding value, and then you can perform better selections. So especially for low heritable trade, and sometimes the animal must be in the disease-free environments. Something like the parents of the animal must be in the system that you need to make sure that there is no any specific pathogens. So most of the time you don't measure the trait or the phenotypes on the parents, but you measure on the close relative. And that actually also makes lower accuracy of prediction of the parents, depending on the relationship between the relative and the parents. So I will give you more detail later about this point. And if you need to measure the trait that is quite costly, this is also problematic at the moment for the breeding program, and all slow down the response to selections. So how next generation sequencing actually help us to improve the prediction accuracies. There are two very important things that we combine together to make genomic selection possible. First, the next generation sequencing-based localizing platform, and the methodology of the used genome-wide predictions. Together, we can do genomic selections. I will a little bit go to a really overview of the genotyping platform first. In aquaculture, for the selective breeding, we mostly have two ways of doing it. Either the SNP array or next generation sequencing-based genotyping. The latter is referred to genotyping by sequencing. Maybe you might have heard about these technologies. Some people say that genotype or GPS, genotype by sequencing, is not the same technology to RADSEC. But in this case, let's consider they are the same at the moment. The RADSEC is the way to actually get a very high density of the SNP markers. Compared to the SNP array, you can also get that. But the comparison between these two technologies already published recently. And you can see that if you perform, you get the genotyping from RADSEC, the complexity of this method is quite high because you need to have bioinformatician to do the analysis for you. Whereas you can get the genotype data directly from the SNP array. And the price is also quite relatively higher for the SNP array compared to the RADSEC. So people still prefer the RADSEC due to the cost of genotyping, but they sometimes struggling with the complexity of the analysis. So the RADSEC is restriction site associated DNA sequencing. It's a combination of genome complexity reduction by using the restriction enzyme together with the next generation sequencing technologies. This approach, we don't need to have any prior knowledge, for example, about the knowledge about the reference genome assembly. We don't need to have that, but it's good to have. There are different kinds of RADSEC, and it's already reviewed. So you can have a look on the bit later. The key implementation or application in aquaculture for RADSEC is the generating high throughput SNP markers used to make SNP array and constructing linkage map or QPR mappings or even genome-wide associated study, so that we can see the genetic architecture between the phenotype, different phenotypes, and also the focus of this talk will be about marker-assisted selection or MAS and genomic selections or the GS. So when we consider the genetic architectures, we mostly have two different architectures. So the variation of the phenotype is largely explained by just a few or major QTMs, or it can be polygenic architectures. I will start with the major QTL first. When the QTL is just a few QTLs mainly explain the variation of the phenotype, we prefer marker-assisted selections. A very clear example is the IPN virus in Atlantic salmon. It's already started, I think, even in 2008, before this paper. The IPN virus is double-stranded RNA virus, and the mortality during the outbreaks could vary from 0 to 100%. So it means that all the fish die. You totally lost the production. So if you're looking at the association between the markers and the phenotype, looking at the graph on the left-hand side, you see the different distribution between just a single marker, the Q, the big Q and the small Q. You see distribution of the big Q. The distribution is mostly in a very low mortality rate during the outbreaks. So the green color in this area. And this is the mortality rate, vary from 0 to 5, and it's 50, 20, 30 to 25, etc. to this interval. So the Q or technical Q corresponding to resistant to the IPMs. Whereas the small Q, clearly that the distribution is much broader and more covered to very high mortality of the IPM virus. So the heterozygous is in between these two distributions. And later that actually the study using the rat sequencing data to also pinpoint the position of these markers again, or this QTL again. They found the position of 21 centimorgan on chromosome 28 that corresponding or associated with the IPN QTL. And it's really quite strong peaks. So you can say that just one marker explains quite a large proportion of the variation of the phenotypes. So today, IPM is not that problematic anymore. They can easily improve resistance to IPM by just a few generations. So by selecting this capital Q and Q or heterozygous small q and big Q, you already reduce the mortality of IPM. I think it's really creative. So compared to if you don't do selection. If the genetic architecture for the animal is polygenic, genomic selection is the method. I can see that it's now 15 minutes, so I have to speed up. For the genomic selection, you assume that there are many QTLs, not just one, affecting the variation of the phenotypes. And you have to assume that those QTL is in LD, at least with one of the markers. In fish breedings, what you want to do is that, and this is the most important, you want to actually make sure that the within family breeding strategy they are not the same, because otherwise you end up selecting the whole family and it's not that accurate. The way to do that is, you consider this. Suppose that you have two families, this family and this family. They are in the environment with disease free, and it's impossible to phenotype them because they must be. If you consider the animal from the same family, they must have the genetic similarity between them. And based on the pedigree information, they have a similarity, half of that or 0.5 in terms of genomic similarities. So if you challenge the animal, you can use the information from the animal to estimate breeding value, and with the similarity of a half, within family animal, they get the same breeding value, plus 5, 5, 5, and 1, 1. So you end up selecting the whole family. But in reality, the few siblings, they share not a half similarity of the genome, but about 30 to 70% of the genome instead. So in reality, the genomic breeding value should not be the same of the for the animal within the same families. So this is the way of genomic selection. So if you have the genomic information, you can use to construct the prediction equation to estimate genomic breeding values and use to predict the selection candidate without phenotyping. And in this way, you increase accuracy. And the accuracy that can be increased is by, you can see that 20% to 41%, for example, Atlantic salmon in marine towers. They now go to full genomic breeding program, which means that they no longer use clinical information. I think I'm getting to the final slide. This is my own study. I estimate the breeding value for uniformity for growth in Atlantic salmon and using the clinical relationship of single-step genomic variation, which means that I combine the genomic information with the pedigrees. If you're looking at the distribution of the breeding value, this is based on the pedigree information, and this is based on the 30 case mix markers. You can see that the distribution of the GEBV within family is much more different compared to this pedigree-based breeding value. And it provides also a higher predictive ability, up to 19%, for example, this strain, and 69.5% for this strain. If this is the truncation point for selections, you actually have much more contribution from different families compared to this one. So to conclude this talk, the next generation sequencing-based genotype has already helped us a lot to implement genomic selections and also enable us to get really high quality and dense genome-wide SNP markers. And also we can make a higher accuracy for genomic prediction and let us make more efficient food production. Thank you.
Thank you for presentation.